Hello, good day, welcome back, and please join in to learn again. We are on the series to learn about embedded system on ARM Cortex M4, and today is day 2. I'm Arupian Karasu. I'm representing on behalf of A2DG, who is in collaboration with IndusLink. I'm presenting you day 2 to you. So if you haven't revised day 1, please go back and review it, and I warmly welcome you all to join in on day 2. What we're going to learn about on day 2. Remember I mentioned in the first day, it's about choosing the right processor. Yes, there is plenty of processors and controllers out there, but as an embedded design engineer, you got the responsibility to choose the right processor fit for your project needs according to customer requirements. So let's see what's involved. Today you will be learning about all this below. You're going to learn in depth about just the processor and controllers that you heard about from last session, and you're going to learn about the differences between microprocessors and microcontrollers, digital signal processing, CPLD, FPGA, SoC, and TPU, and about selection of the packages and how to choose the processor. There is a selection criteria. You need to look for those to choose. And you're going to see the software design flow and the hardware design flow, and finally with the 3 design process that's involved in the design process: simulation, evaluation, and emulation. So please go and grab yourself a drink, and I'll see you shortly. Okay, let's move directly into learning about types of processors and controllers. As you can see, the first one of the rank is the microprocessors and the microcontrollers. An example for microprocessor is 8051, and for the microcontroller it's 89C51. The main processing manufacturers for microprocessors are Dallas, Philips, and Freescale, and for the microcontrollers it's Renesas, Texas Instruments. And the microcontrollers comes with 8-bit, 16-bit, and 32-bit. The second one of the chart is DSP, digital signal processing. The main manufacturers are Dallas, Analog Devices, Motorola, and I've given you a Blackfin as an example of DSP. The third one of the list is CPLDs or FPGAs. CPLD stands for Complex Programmable Logic Device. It's obsolete for now. Most companies and most new designs are using FPGA, so you're going to learn about all of that shortly. An example for CPLD is Lattice. An example for field programmable gate array is Xilinx and Altera. Xilinx and Altera are two processor companies for FPGA, but now a bigger company like AMD acquired Xilinx and Intel acquired Altera. The next one of the rank is general purpose process and central processing unit. The main processor manufacturers are, as you can see, it's Intel, AMD, and for general purpose process, and for GPU it's NVIDIA. Then we're going to see about application specific integrated circuits. A major manufacturer there is ASIC. For ASIC is Intel, sorry. Next one of the line is SoC, system on chip. The main manufacturers are Qualcomm and Broadcom. The last one of the list is TPU, that's Tensor Processing Unit. Google developed its own device called Coral, and you're going to see about that in the next coming slides. So just to give you briefly an outlook about how many processes are involved out there, I strongly suggest you to go into this site where you could look for the microcontrollers. So there is a supplier site called digikey.in. If you go in there, you can see for yourself what are all the available microcontrollers and DSPs, etc. So on the search bar, you can type microcontrollers, and hit enter, and this will populate all the available microcontrollers. As you can see, there is 88,392 items out there. So if you want to dig deep in, just click on the microcontrollers, and this will give you the whole list of what's available in the market for you to use in your projects. And as per the customer requirements, you can go in here and have a look, and possibly choose one processor that suits for your specific needs, your basic and benefits. It's loading. Just give me a sec, please. Once it's loaded, you can filter it like this. So these are all the manufacturers, and these are all the packaging, and you can see the core processors, the core size, again the speed, how fast or how slow the processor works, so you can filter it by that way. And also the connectivity, the peripherals, as you can see. So this is a really good site if you want to get more research into it. When you want to choose your processor, I strongly recommend you all go through this digikey.in, and you can type in anything as you like, and you'll get the research. Okay, let's put this aside for now, and let's get back to what we're going to learn about today. So as you know that these are all the available processors and controllers out there, and thank you for Pantech Pro Labs for pinching me for me to use this picture. Thank you so much, and we're going to see next. Now we're going to get deeper into all the microprocessors and the ones we saw from the last slide. Now we're going to see about microprocessor. Microprocessor is a processor which has a central processing unit that is designed to perform general purpose computing tasks. And as you can see, all the other peripherals are outside CPU, so that means each and every individual module, the boot startup ROM, the program ROM, the data RAM, transducers, the keypad UART, all this you need to make a specific PCB design, and you have to interface to the CPU. So that adds a lot to the cost, because you need to design each and every individual module, and you can communicate that via the control address and data bus. It is advantageous because you can keep on extending if you want to have further peripherals added, which is a really good point. So the microprocessors are designed to perform general purpose computing tasks, which has all the arithmetic operations, logic operations, and data transfers. Next we move on to the next one of the line is microcontroller. What is a microcontroller? A microcontroller is a small computer on a single integrated chip, as you can see, to control a specific system or a device. As you can figure out yourself by the name controller, it is a device that's used for controlling a particular task, a particular activity. So what is a plus in the microcontroller is everything is embedded inside the chip. So you don't have to go out and design extra PCBs to integrate, to communicate with it. Everything is included in one single chip. So the UARTs, the program memory, the data memory, the parallel ports, the timers, ADC, and the CAN peripheral. So everything is built in, and this is what you would see when you do the DigiKey search. You would see like this. So everything is built in. The one drawback is everything is limited because it's all inside single chip, and again it depends on your project needs and as per your customer requirements you can pick and choose, but there are plenty of variations, right from 20 rupees to up to about 10,000, 20,000, even lakhs, for one single microcontroller. In terms of dollars, it's about $3 to say roughly about $100 that's available there. So where is microcontroller is specifically used? These are used to control a motor through the motor control system on a sensor interface, and can be also used in a display unit as well. And before we see the features, I'll say what is DSP. DSP is a specialized, DSP stands for, first of all, it's digital signal processor or processing. DSP is a specialized microprocessor that is designed to perform high-speed mathematical manipulations and calculations required in signal processing applications. It is mostly used for data processing. So if you take as an example as a audio or a video processing, the image and the video that you're seeing, this has to process through. So everything comes with frames per second, so that has to process and has to process really fast, so you can see without any stallings, like I'm there next to you and talking to you, so that sort of speed DSP gives that. Can be used in DSPs in communication systems and in control systems. And DSP are really good in running with real hard time constraints. So as you know from the previous session, that real time constraints are the ones that a task meets or performs or completes to a desired time, to a specific time. That's called real time. And hard real constraints are even major. When something goes wrong, it leads to catastrophic issues. So that's where DSP is highly regarded to use. And DSP usually processes continuous infinite streams of data. So no matter what, it keeps on processing on the behind the scenes, so you would be able to process your image and your videos. And one big thing is it has its MAC capability, multiply and accumulate. So you can do multiple multiplication add-on applications pretty much faster than anything else. Um, in one single instruction cycle, it can be processed, so that's why it's MAC. And DSPs are designed to perform high-speed mathematical calculations, such as it has to pass through a few phases of filtering, modulation, and demodulation. And through this, the DSP comes in handy compared to the general processor. So the DSPs are used to solve complex mathematical calculations where floating point unit as the key in there. Floating point unit in the sense when you check for image and audio and video, it is about the precision, so you can get into the precision of that. So that's where DSP is really cool to use. In order to use the DSP, it comes with different architectures. For widely, what I'll show you, I will tell you about the architecture in the next one, but let's see, why do we need DSPs? DSPs are data path oriented, as I said in the previous slide, that when you do about video, image, and audio processing, it's after data, so it's more oriented with fast processing, so the speed is enormous compared to microcontrollers where it's only controlling specific activity. A GPP processor is used when there is a large requirement for larger memory, and on advanced operating systems, this is the desktop and PC where the memory is into consideration, where it needs a lot of storage. So the DSP processor is really handy when the requirements are for precision, and it's a lot cheaper compared to microcontrollers. and compact in size, and also works in very low power, 3.3 volts, and process continuous data signals, so it can be used in real time. So these are the major ones. As I discussed to you just shortly ago, the DSPs are formulated along these two architectures that's widely used out there in the industry, and the ARM architecture that we're going to cover up in this series is Harvard architecture. So architecture called Harvard. So Harvard come up with this architecture to process between the CPU to the memories. So what it is the CPU is connected to the program memory and the data memory on a separate bus. It has its own address bus and the data bus. And what that is advantageous is at any one single instruction at any one time, you can access to both program memory and also the data memory. So which is really handy when you work in complex large projects. Whereas there is another architecture called von Neumann architecture. Some of the microcontrollers are based on von Neumann architecture. The big drawback on that is the CPU is connected to the data memory, program memory, and those memories through on a single bus. The same bus is used to communicate. So the disadvantage is you can either fetch only program memory or data memory, so that slows down the process. So that's where DSPs come in handy, where they use the Harvard architecture where you can use both. So now let's jump into CPLD architecture. So CPLD architecture is complex programmable logic device architecture. When you want to recreate a lot of I/O peripherals into your project, that's when we go for CPLD, where you can use a large number of input-output terminals. For example, in microcontrollers, due to the limitations of the pin, for example, 8051 comes with 40-pin IC, and it has limited usage of the pin to use only 2 UARTs. Whereas if you use a CPLD, you can almost configure every pin as to be used as UART. And if you want to use 10 UARTs, yes, you can use. So CPLD is specifically designed for that, to use the complex logic functions through the form of input-output peripherals. So what is CPLD? It is composed of a lot of PLDs, programmable logic device, that holds the logic functions, all your basic logic gates, your Boolean algebra functions, all in the PLDs. And it has logic blocks, as I said, can be converted to your own peripherals. Like if you want to use 10 UARTs, these logic blocks can integrate with the I/O blocks. So the one on the yellow, which is on the outer boundary, is the I/O blocks. And clock routing is the one, it gives clock to the PLDs. And there is a routing matrix which connects the PLDs with the next PLDs through a matrix, if you feel like. It's all networked. So this is basically about the CPLD. And now let's get into the next one. So it said it's traditionally used for implementing logic gates. So the next one of the rank is FPGA, and we're going to see its architecture. FPGA stands for Field Programmable Gate Array architecture. So what is there in there? The main advantage of FPGA is you can customize as per the requirement changes from the customer after manufacturing. So it's highly configurable. So if the customer wants to add on more features, the FPGA can do that. So that's a key plus thing to use FPGA architecture. And like CPLD, this has all the basic blocks that we saw there. It has its logic blocks, it has its I/O blocks, it has its clock routing, which is the clock that you give to logic blocks, and a routing matrix which connects your neighboring devices. On top of that, it has its own memory for extra storage, and also it has its DSP. That's where the memory and the other module is connected. So, and there is a multiplier which has the DSP block, so you can actually integrate a DSP in a FPGA for your audio and video applications. Now let's see what are all the FPGA technologies out there. The first one is the static RAM technology. It is reprogrammable and it is volatile. So what does that mean? When if it is powered off, the internal program memory gets erased. So that means you can't use it again until it gets programmed. So that's why it's a reprogrammable FPGA. The real good one we use in the industry is Flash. It is best of both worlds. It is reprogrammable and also non-volatile. Non-volatile is even when the power is switched off inside the memory, the contents holds its programs. So you don't have to reprogram again to use it, but if you wanted, you can overwrite it. So Flash is one good tool, and there is another one called anti-fuse technology. Anti-fuse is only used for one purpose. So once you program, you can't erase it or you can't modify it. So that's anti-fuse, and anti-fuse is non-volatile as well. So when to use DSP in FPGAs? If you consider all these three, that's where DSPs is a very good fit in FPGA. When you think about higher performance, because parallel programming algorithms happen at the same time. Audio, image, video, everything happens, so it gives you a high performance. And also the design can be customized considering the speed and the cost. And being the above two considerations, it reduces the number of chips, and that reduces a less number of chips. And as design engineers, we talk about real estate. Yes, the lesser board space, the less money it's going to cost you to make it. So the less chips, it's better for you. So that's where DSPs come in handy. Okay, let's move on to, I would like to show you how those days the traditional way of embedded systems using a DSP. As you can see, this is a TMS 320C6711. This is a traditional embedded system using DSP, which has all these modules. It has Ethernet, it has CPU, audio codec, power supply, timer, interrupt controllers. It has the memory, SRAMs and SDRAMs. It has the display controller, the logic circuit, the memory controller. So everything is there and occupies a lot of space in one single board, and everything adds cost to it. So how are we going to use this to a reduced design when you move forward with the FPGA? So how we can reduce is the power supply unit that's used in this last traditional photo that you saw dissipates plenty of heat, so therefore it reduces the performance of neighboring devices. So that can be removed and can be connected from outside. And the traditional way of embedded system used as an audio codec. FPGA is mainly digital, purely digital, so the audio codec can be interfaced from outside the FPGA. Audio codec has the functionality to cover the mic and the speakers, so mostly the signals are analog, so it can be moved outside. And also you can move all the memory elements for storage when such audio processing or image processing happens. That's where it's stored. And these occupies a large space of silicon area, so that again it needs space in your board. So you can remove all of that, and the logic circuits you can move outside. So removing all of this and changing to a configurable SoC, so all those now external, and you can still communicate through the bus like that. So what it does is it gives you that processor speed, so it acts quickly and it's compact and configurable. So this is where the system on chip concept started. So everything combined or fused into one single chip. That's basically SoC is. And as this man is holding, that's a kind of SoC that you will see in the market. When we talk about SOC, it is about multi-core processing. Multi-core meaning two or more process in one package. Like in this example here, this is one full package which has the ISP, the image signal processing. It's got general processing unit. It has got multimedia, DSP, CPU. So everything is built in is more than one processor in that to perform its operations in one cycle. And when it comes to multi-core, there is two divisions. One is symmetric and asymmetric. Symmetric is if you have number of identical processors in one single package, then that's symmetric. Whereas if different processors like this are used, it's an asymmetric processor. Being symmetric, you can use the same memory commonly used, but being asymmetric, you can't have enough space to use the memory, so possibly you can't have the same memory usage. And being symmetric, just one operating system is all you require, and you can perform that processor. But being different process involved, so it can run a Windows, it can run a Unix on the same package, so it needs dual operating system or different. So this is about the SOC. So I've given you an example to that SOC is the TI OMAP series. The OMAP 44X don't have identical processors. This is due to there is an increase in the chip performance, so the processors are specialized like this to use the chip performance. So in this example, there is ARM Cortex A9 is used as a primary core, and that does all the basic arithmetic and logical operations for the processor to perform. And there is a separate processor where its image is processed through ISP, and there is another processor to control all your audio applications, and there is another one to control your video applications through this HDMI port. So these are all having separate, like for GPS, there is a GPS, the Bluetooth, the modems, 3G and 4G, the memory cards, the USB. So everything has its own process. So by dividing all this, the processing speed is really fast because multiple things gets done at the same time. So that's why the SOC is really popular among the industry and the designers. So now we're going to talk about and the SOC emerged as competition between the DSP to the FPGA. So they come up with the SOC. So that's why the SOC is really so popular. And now we're going to talk about the ASICs, how it is going to be different to FPGAs. FPGAs, as you learned from previous slides, it can be field programmed. The internal functions can be modified according to customer requirements if they want it, but it doesn't emulate its own custom circuits. A good example is Xilinx Spartan XE3S compared to the ASIC. ASIC is application specific integrated circuit, which is targeted to perform that specific application. It is a special purpose built. Once it's manufactured, you can't do it for any other application because that's where ASIC is popular. And if you want to produce it in large quantities, ASIC is the way to go. And this is the example I've shown. Company Samsung has okay, you can say that way. A company in Canada called Square combined with Samsung, and they come up with a Bitcoin processor. So this processor, that K4D55, it's a Bitcoin processor to use just the Bitcoin operations. So as I said, once built, the internal functions can't be modified. That's why there is a bit of a restriction with ASICs. Then we move along to TPUs, the tensor processing unit. The tensor processing unit Google come up with to accelerate their AI integration to their units. So this is an extension to their ASIC development. So it can be used in neural networks, machine learning. So to do that, they come up with their own software flow, and they use TensorFlow for that. So mainly developed for a third-party use, so the third party can buy this and include in their cloud infrastructure. By doing so, they come back to having their small chip where it can be designed for um, fast processing with low precision computation with more IO operations. So that saves a lot of energy per joule without a big mapping for big hardware. So this is the device, so just tiny, and it can sit on basically on top of a heatsink assembly. So you don't need a big space to install or fit in. So in a nutshell, to compare all this between the cost versus the performance, um, just for a simple project, if you want to say for example employer wants to come in through the door and he taps a card, so things like that, the tapping just makes it to open the door for the employee to get in. So the microcontrollers, even 20 rupees or 50 rupees microcontroller will do that, compared to FPGA where it can be customized and it can do multiple processing at the same time with the DSP, that audio and video application. So therefore the cost is very high and the performance is right out there, and as you can see the others are in between with the comparison. So the FPGA is the go-to with the embedded system, and you will learn more about it as you get into the industry. Okay, now we discuss about choosing the processor. What are all the real factors that you really have to worry about? It's about the processing power, how much processing it needs, like how faster it can do your work in one single instructions, like 100 megahertz processor to a 200 megahertz processor. And power consumption, can it work on low voltage which don't consume a lot of power, and cost, how cheap it is compared to the other process, and the availability and support. When you consider this, it has to be available for the next few years, otherwise your design will go stuck and you won't get any support after support. So that's the major problem with that. And the connectivity, how are you going to integrate with other modules, and the size and form factors, and the security, how secure is your processor not to be forged by any other things. Now we're going to talk about the selection of packages. As I kept saying from the first slide, so the processor and the controllers, the DSPs, FPGAs come with packages. So there are a few packages that I shown you here. DIP is a dual inline package, which is two rows, got protruding pins like that. QFE is quad flat package. SOIC is small outline integrated chip. PLC is plastic lead chip carrier. BGA is ball grid array. The most of the FPGAs are ball grid arrays. So if you want to mount this BGA, you can't do that with simple soldering iron or soldering station. You need an oven to certain amount of heat it needs to solder and mount it. So that adds to the complexity of the and also the design. So the cost involved. Whereas a small dip chip, you can mount it through a soldering iron. So that's why you need to be really careful in picking the package, thinking cost and what's involved, the work involved. So this is about the packages. And how are you going to select the processor? So there are some benchmarks that you have to look for to select this processor to make it work and effective and efficient. First, you go with the development tools. What are all the development tools out there? And you're going to, as a design engineer, you're going to come up with your own research and discuss with the client and come up with the development tools. And the hardware tools, if you use BGI, then you need to buy oven, so there is extra added cost into that. So you need to comply with that as well. And the power consumption, can your design be operated on low power with battery, for instance, so you don't have to connect this to the AC all the time to make it work. So like that. And the number of IOs, how many IOs you need to connect to your neighboring modules. And the performance, how fast it can perform compared to 100 megahertz to 200 megahertz. And once again, the cost is involved due to the performance. And the operating systems, whether does your system need a real big operating system like a real-time operating system RTOS, or can it run on a simple program, and the number of peripherals you need to use. For instance, if your microcontroller sometimes doesn't come with CAN peripheral, then you need to get the CAN peripheral as a separate chip, and I need to integrate that to the main system, and that adds more complexity and a lot of toing and froing. And the main thing is supplier reputation. You have to keep this in mind. This is really key. Your design, your project should prolong as long as you can for the next 5 to 10 years. So the after support is really necessary for you to maintain your design. So talk to your local manufacturing and assembly houses, and they have a better idea about the supply, because they on a daily basis talk to the suppliers and they know what's out there. So these are all some benchmarks when you sit there and choose which processor is best for your project according to the customer requirement documents. So these two you need to tally on every day. You need to go through every time to do this. Now I'll give you a short break, and then I'll come back and explain to you. There's not much more to do to learn today, I mean. So after 5 minutes, I'll go through with you the flows. So see you in 5 minutes. Catch ya.